Very happy to introduce Professor Mohamed-Slim Alouini from the University of Science and Technology of Saudi Arabia. Short, we all love to call him Slim. He has been a champion of connecting the unconnected for many years, and he is globally unknown. And he can be seen in any event that's happening on connecting the unconnected. So we're very happy to see him. Recently, there has been a lot of interest in the satellite and apps and those kind of technologies. So his talk is going to be on tapping into the full potential of the stratosphere, and we are very happy to have him here. He was born in Tunis, Tunisia. He received a Ph.D. degree in electrical engineering from Caltech in 1998. He served as a faculty member at the University of Minnesota, then in the Texas A&M University in Qatar, before joining in 2009 KAUST, where he is now a distinguished professor of electrical and computer engineering. Professor Alouini is a fellow of the IEEE and OPTICA, which used to be known as OSA. He is currently particularly interested in addressing the technical challenges associated with the uneven distribution, access to, and use of information and communication technologies in rural, low-income, disaster, and artificial changes. So that was the
Thank you, Luis, to you and to Prof for inviting me and for giving this opportunity to share with you some of our ongoing work. I was checking the title that I shared with you, that's why I was looking at the program. Okay, so I changed the title slightly, but the theme is the same. So the title is above the clouds and below the orbit, basically the stratosphere, 20-kilometer altitude from the ground, and how this particular space is or has a great potential to offer a sustainable and prosperous future for these high altitude platform stations to connect the unconnected and do many more things. So obviously, the context is like many of my colleagues, some of them present here. We are working on 6G. 6G, of course, like all previous generation of wireless communication system, is going to push the envelope in terms of speed, in terms of lowering the latencies, in terms of increased density of connected device per meter square. But 6G also, in contrast to the other or earlier generation, set as a goal to basically connect more of the unconnected. I'm glad that we are having these kind of meetings to share some of the progress done in this context. Obviously, you know, I think this morning we had a great presentations and the reasons why we are having this connectivity divide. And one way to kind of summarize one aspect, which is a technical / economical aspect, is by looking at this diagram. This diagram is showing the quality of experience, let's say, in terms of latency or data rate, as far as the cost per user. And here we are focusing on the rural area, which tend to be low density. We know optical fiber is the way to go for urban environment, but when you go for this rural, sparse populated environment, what you need to achieve is this upper left corner. What you want to get is good quality that is affordable, and that's a challenge that we are trying all to solve. And obviously, one way to achieve that is by gaining in altitude, by doing things in a completely different way. We do it in highly dense urban environment where we densify and put more and more of these base stations at a relatively low altitude. We want to go into higher altitude. And by the way, and I think this has been touched upon in many of the previous talks, but I would like to emphasize that. And when we do research as researchers, at least in this area, of course, we are looking at this connected and connected. And the first thing that comes to your mind is rural areas, developing countries, but actually you are touching multitude of other sectors. For instance, disaster or post-disaster and emergency communication, when basically you have to deal overnight with hundreds, if not thousands, of unconnected people because the ground infrastructure has been destroyed. And so from the space again, and we'll talk more about satellite and hubs, can be a great way to bring the temporary network to address these issues on a rapid fashion. Exploration, when you send scientists exploring the middle of nowhere, Antarctica or Amazon, and you want to stream, that's of course an important problem of connected and connected. Military missions often also operate in this kind of unconnected environment. Another topic that is often, I would say, forgotten or neglected, when we say about connected and connected, yes, primarily we are talking about people, but actually once that umbrella is there, you can start connecting all kinds of IoT devices. And in a way, you kind of go from the narrow concept of smart building and smart city to smart rural areas, smart villages, smart living. So it enables much more intelligence, not only in urban environment, but rural environment where you can use that for environment monitoring and smart agriculture. There are other applications that like special events where we have like a need for an extra capacity for a short period of time, like a final of a match or Olympic game for 2 weeks. We need extra capacity only for this field. There is no need to current capacity. The for non-intensive network is a great application. And finally, emergent three-dimensional network. We're talking here about eVTOLs and flying taxis and so on, can also benefit from connectivity from space. So research again in this area can essentially address multitude of other sectors beyond just connected and connected in the classical way people understand that. So obviously, from an infrastructure perspective, and especially when we talk about underpopulated or sparsely populated areas, satellite has been the big breakthrough that we have seen over the last few years. And when we talk about satellite, and I think this morning we had a great talk by Professor Said Rahman, where he gave all these solutions. When we talk about satellite, yes, we know Starlink, we know the mega constellation, but we have to remember that satellite have been there with us for many decades with the geosatellite that offer also quite a good service with a certain latency. And there are still ongoing, basically, satellite projects, so Starlink, one of them, but we have the Amazon Kuiper, the Chinese GW-G60, Canadian Lightspeed in the making. European Union is trying to launch their own mega constellation known as Iris. So it's a great kind of evolution that we have seen, and there is a promise that over the coming few years that we are going to see more of the Starlink around us. But now I would like to start my part of the let's say, or my focus in this talk by starting with this argument. The argument I start with is that we don't live in a world where population density is binary. We don't have downtown area with super high dense population and deep rural area with very few people. We have all kind of environment in between. And the argument that is backed up by some of our papers that we are putting forward, for this different dense population, we need base stations that are attached to different platforms. In other words, satellite is not there to solve all kind of connect the anchor problem in all kind of dense population. There are dense population where satellite will not be enough. Why? Because we can keep densifying this kind of constellation. That's happening now. We're asking for an extra server capacity fee for the customers because they're living in the area with a lot of demand. Whereas actually the way to do it is by going to a lower altitude and offer the right capacity to that population of people that is actually in a mid-density population scenario. That leads us to this concept of using base station stratosphere. Again, this is not my own. I'm just kind of active in this research area. It had been proposed over the last, I would say, 15 years as a solution, if not earlier. So what are these platforms? They are known as high altitude platform stations, known also as high altitude pseudosatellite. The acronym is the same for these two terminology, HAPS. They come in different shapes and forms: balloons, airships or blimp, if you will, or classical aircraft or drone or glider, if you will, that are illustrated here. They are supposed to operate in the stratosphere at roughly 20 kilometer altitude. So they are not, and that's why I said above the clouds, below the orbit. They are not on the orbit. They are on quasi-stationary type of trajectory because they cannot stay just on a fixed location. They have to hover somehow. So they will do a circle or an 8 over a limited region. And the vision that we have for these, I will not even call it base stations, but really infrastructure in the stratosphere. This morning, one of our speakers, Mike, I think, was talking about company that specialized in towers. I believe 10, 15, 20 years down the road, we'll have companies specializing in tower in the stratosphere. Their objective is to just bring the infrastructure and make it up and running in terms of giving the right power, the right endurance, the right coverage. And then telecom is one application among many. Once you have a tower at 20-kilometer altitude with that kind of visibility and coverage in a quasi-static fashion, you can attach a radar. So if you have like a disaster, like illustrated here, you can try to measure in real time the level of water. You have a refugee camp, people have moved because of this disaster, and you want to connect them. You have basically here a camera that can be used for border control with super high resolution, much better what any satellite can do. You can have a LiDAR for imaging purposes. So you can think what you can do. In a nutshell, being at 20-kilometer altitude, much lower altitude than the LEO satellites are 500, 550 kilometers, you have a much better budgeting. And in a way, you can do everything satellite can do better because you are closer to the ground. Now, I don't want to spend a lot of time giving you the argument why HABs are great, and satellites are great too. I'm not saying, I'm not trying to put them in competition. We wrote a paper recently where we say the 3C paradigm: the collaboration, the coexistence, and sometimes the competition between HABs and satellites. But let me give you two arguments where I would like to emphasize why we should look at HABs. The first argument is a very simple argument from physics or from budgetary calculation. Again, when you are at 20-kilometer altitude and you want to solve a direct to cell, people have been talking in this workshop and in many conferences, how do we connect direct to our standard phones, right? That's what every single mobile network operator is trying to do. And when we say connect to standard phone, we are not talking about texting, broadband connectivity. That's not an easy problem when you do it from 500 kilometer altitude, especially for the uplink, because you have just one antenna. Or the phone trying to talk to a HABs is much more easier to achieve rather than trying to have this huge antenna in satellite. That's argument number one. And argument number two is a sustainability argument. If you want to rely only on satellites to cover all kinds of dense population, there are areas that will require a high density of satellites, which is densifying this constellation further and further, going beyond the hundreds to the thousands, to maybe the tens of thousands of mega constellation. And that's not sustainable, because there is a risk of collision. You all know about the Kessler paradigm that can happen. One collision can generate debris can generate more collisions, and you can see the avalanche effect that can happen if we see more and more these collisions. So bottom line, some problems have to be solved at 20-kilometer altitude, and HABs are there to solve these problems. Now, I see there probably a few minutes. Let me tell you some of the research. What kind of research telecom engineers are doing in this space? A few of us active in the area of stratospheric communication or HABs communication. One problem is, and Monisha will talk about spectrum, and this is a different kind of spectrum sharing problem, is the coexistence between terrestrial and stratospheric, basically, networks. So we go with the assumption that a few years from now, we'll have these HABs. These HABs will coexist with our terrestrial network, and they'll be using the same spectrum. That's actually one of the main wins of the HABs Alliance, which is like a kind of alliance that kind of group all the active research, not research industries and academics, but mostly dominated by industry and HABs. One of the main game that was done in WRC, the ITU WRC 2023, is that a lot of the IMT band that are allocated to terrestrial network have been also allocated to the. And the idea is you want to use the same phone. You don't want to have phone operate on different frequencies. So basically, it's now, well, that's nice. This is the kind of thing we'd like to see. But the problem is, of course, this is going to lead to some spectrum to some level of interference. So this is like the paradigm that we are solving in this paper that we just finished. Is going through the review process. So let's assume you have a province. In this province, you have some communities. These communities are well served by 5G terrestrial network, but in between, the gaps that are in between are going to be covered by this upper architecture of hubs, basically base stations. Now, what can happen? So first of all, so it's a stochastic geometry-based analysis. I would like you to focus on the left graph. And first, let's look at only the dash curve. When you look at the dash curve, we have 4 categories of users. Deep urban, urban close to the rural area, rural close to urban, and deep rural. The black here, yes, so basically these are the 4 categories of users. You assume you have a city, and you have these 4 categories of users. When you have no hubs, without hubs, you see that basically the deep urban, the users who are in the city close to rural area are doing fine. The rural users that are basically close to the city are still benefiting from some of the base stations that are well connected and available in basically the city. But by the time you go to deep rural, the coverage is 0 because there are very few base stations. This is based on our model, of course. You introduce the hubs on the top of the terrestrial base station. Of course, the deep urban are still doing well. We assume here that what we call uncoordinated system is a system where you connect based on your location. If you are in a city, you connect with the terrestrial network. If you are in a rural area, you connect by default to a hubs network. What happens? The urban users are doing fine. The urban close to rural area are doing fine. The rural close to urban environment are still doing fine. What happens is that the urban user, the rural user close to the urban environment, these ones, degrade significantly from a coverage perspective, performance. Why? Because they start seeing a lot of interference coming from the terrestrial base station from the neighboring city. They are connected to the hubs because they are outside the city, but then they are still quite close to the city and they are getting all that interference. The deep rural user, on the other hand, getting a great boost from 0 to something that is much better. How to address this problem? You need to introduce some coordination between these 2 layers. And the coordination can be done as simple, and we can do it in a much more sophisticated way, by basically allocating to the user the best channel at any given time. So you may end up connecting to a terrestrial base station while you are still in a rural area, but not very far from basically the downtown area, and vice versa. You can be in a city, but connect to hubs because it happens that you have a better line of sight from the hubs from wherever you are. When you start coordinating these 2 systems, right away you can see benefits for all categories of users. You conserve like basically the good behavior of all the urban and nearby urban users, but you still give the hubs the opportunity to basically raise the performance of the deep rural users. Now, in a nutshell, this is the vision we have for 10, 15, 20 years down the road, when we have this stratospheric network available to us. They will be creating a similar network, but not on the ground, but rather at 20-kilometer altitude. Free space optic is another interesting emerging technology that will be very beneficial in this context because that can give you a highway of high-speed information for these kind of flying platforms. And of course, you will have to use beamforming and MIMO technology, but not now from the ground, but from the space to connect again, I would like to emphasize, not only to users or people, but also all kinds of IoT devices. So with that, I would like to conclude with this 2 statements. Number 1, HAPS has a good future, and argument number 1 is a sustainability argument, because I think satellite constellation cannot keep growing without a limit, and we need to start using the space in between, which is above the cloud, below the orbit, and I think time will come where we really realize that this is to happen. And of course, as I mentioned, I don't see this as just a connectivity problem. This infrastructure, once it will be there, it will be useful for many more applications, the same way we use satellite for many more applications. With that, I would like to thank you. So, you can follow some of our research activities. We have a research group, a website. My students often do video on the YouTube channel of our group. We have established a couple of years ago a UNESCO chair focusing on this problem of connected and unconnected. We have a LinkedIn page where also you can follow some of our papers and research results. And with that, I would like to thank you, and I will be happy to take questions now or during the break time.
Maybe during our break.
I can count.
Okay.
Okay.
The people on the Zoom.
Thank you. Very interesting, Slim. Question is, stratosphere balloons, drones can live for a few months. Satellites live for tens of years. How do you replace them every 6 months? Have you talked about that idea of
Actually, excellent question. This is a blessing. If we reach few months, that's great. We are now, by the bottom line, we are now at a time where mega constellation were 15 years ago. A lot of activity, a lot of startups, big players like Airbus, Boeing, trying to do these apps. But why I see it's a blessing 6 months? Because what is the problem with satellites? Once we send them, they are there. If they break in the way, that's it, send another one. A HAPS, it's an aircraft. It goes there on a mission. It's supposed to come back after a few weeks or a few months. It can be maintained, it can be upgraded, but more importantly, eventually it will be retired and it will not become a big group. So the fact that is a finite time is, I think, a great advantage perhaps compared to satellite, because of the fact I meant for the 3 facts I mentioned.
You have a company we can invest in?
No, not really, but we have a HAPS Alliance. I'm a member of it. I'm an academic member, and there are a lot of good players that are really doing some progress with different technologies. Some in the US, some in Japan. It's not easy. I'm not saying it's easy, but I think the problem eventually will be solved. Because, and once it's solved, it's going to be disrupted. The same way Starlink was disrupted for the last few years.
So I know you have just a quick question, please.
Yeah, it's a quick question. I can foresee that if you have a disaster scenario where the rest of the networks are not available, this is a great solution. But as a sustained network or as a ad hoc network that is deployed, it does raise issues about interference and coordination with the existing networks. I don't know how far you have looked into that.
So let me answer this. Definitely, post-disaster emergency communication is the short-term kind of hanging fruit.
Yeah.
And if you see who are some of the big investors in this technology are Japanese. NTT Docomo and SoftBank. Why? Because they think that this technology can be started being deployed. We are talking a couple of years from now, they invest, for example, in Zephyr, which is like Airbus type of essentially for this post-disaster emergency communication. So that's the short-term object. In the long term, again, I don't look at it only from a telecom perspective. I look at it as a solution, a tower at 1 kilometer altitude. And like we are solving now the coexistence between satellite and terrestrial network, the problem of coexistence between the stratospheric, basically frequencies and ground frequencies is, and this is on the table. And the last WRC, World Radio Conference ITU 2023, it was discussed. And a lot of the IMT band have been given to the HAPS, and that's why we are looking at this problem and see how we can address it with MIMO technology, with kind of interference construction technology, so that when this technology will be ready, we'll have solution how to deploy.